Probabilistic models let us reason about uncertainty by assigning likelihoods to outcomes. We'll focus on naive Bayes, a simple fast classifier that assumes features are independent given the class. After the theory, we'll work through concrete examples to build intuition. Naive Bayes models prediction as probabilities. Inputs and output are random variables, often Bernoulli, categorical, or Gaussian. It is interpretable through its hypothesis, loss, and optimization. Using Bayes' rule, we compute the posterior from likelihood and class prior, assuming conditional independence, which simplifies computation. For example, we can compute the probability of an unlabeled document to be one of few categories like technology, business, arts, etc. So when we classify a document, we pick the category with the highest posterior probability. The overall probability of the observations, or the denominator, does not depend on category, so we ignore it. An important assuming is the independence of words, allowing us to multiply each word's probability as shown in the known likelihood. An easy-to-understand example of naive Bayes is to detect spam by turning each email into features, words like free or urgent, then learns how often each word appears in spam versus non-spam emails. For a new message, it computes spam and non-spam probabilities and labels the message as spam if spam probability is higher. Next, we look at an example. In this example, we have 5 Vive documents in the training set and 3 in the test set. This is a very small example, and only good for understanding how to classify a document as one of 2 categories, SAM+ or I+. So from the training data set, we compute probability that a document is SAM+, that is 3 out of 5 documents. Also, we can compute probability of a word SAM, given that the document is from SAM+. We find that there are a total of 13 words in SAM+ documents, and 7 of them are the word SAM. Similarly, we compute all other probabilities. There are 3 types of classifiers we can use in making probabilistic predictions. Random classifier guesses a label uniformly, so it succeeds by chance about half the time if there are only 2 categories. This is good for distributions with class balance. Max always picks the most frequent class, giving a 2/3 success in our example. This is good for data sets with heavy bias towards one class. Naive Bayes uses conditional probabilities to make smarter predictions, though it can be computationally heavier. Let's look at another example now. To play or not play golf given certain conditions. In this table, we have a data set based on attributes like outlook, temperature, humidity level, and wind conditions, dictating whether one played gold or not. We can compute several prior probabilities from this data. Played golf given high humidity is 3 out of 7. That is, if you look all the 7 humid days, you played golf 3 times. High humidity given you played is 3 out of 9. Not playing on a sunny day is 2 out of 5. Sunny days are 5 out of 14. These examples show how past data helps predict play decisions. Now we create 2 tables, frequency, and then from the likelihood tables for outcome yes. Turn counts into likelihoods by dividing each outlook count by its class total. Sunny given yes is 3 out of 9, about 0.33. Prior yes is 9 out of 14, about 0.64. Applying Bayes yields posterior yes given sunny near 0.6. Similarly, we create the tables for outcome no. From the counts, the likelihood of sunny given no is 2 divided by 5, or 0.4. The prior of no is 5 over 14, and the chance of sunny is 5 over 14. Applying Bayes yields the posterior probability of no given sunny as 0.4. These tables convert counts to likelihoods by dividing each column by its column total. For example, sunny is 3 out of 9 for yes and 2 out of 5 for no. Repeat for humidity, temperature, and wind to get probabilities. Now to answer the question, should we play or not on a rainy day with cool temps and high humidity and windy? What would the naive Bayes recommend given these conditions? Using naive Bayes, we multiply feature likelihoods and the class prior for both yes and no. For rainy, cool, high humidity, and windy, if the calculated probability for no is higher than for yes, so we predict do not play golf under these conditions. Try it yourself. Naive Bayes, although highly interpretable, should be applied carefully. Avoid naive Bayes when features are strongly dependent, feature-to-class relationships are highly nonlinear, priors are unreliable from limited data, continuous variables are non-normal, classes are imbalanced, unseen categories appear, or dimensionality is extremely high. enjoy creating probabilistic models.